This meeting is being recorded. This meeting is being recorded.
Okay, screen is visible.
Yes, sir.
Okay, so from this unit, okay, this last point is remaining. But before going to the last point, we will just brush up the few concepts that we have discussed in the last lecture. Okay, so the power consumption analysis of CMOS circuit we have discussed. There are two types of power consumption, right? Static power dissipation and dynamic power dissipation. So what are the causes for this static power dissipation is leakage currents and other static currents. These are the main uh, cause that leads to a static power dissipation. Now talking about the dynamic power dissipation, it is mostly caused by the short circuit currents and output capacitance. Okay, so now how to calculate the total power? So total power is equal to PS plus PWS plus PSC. That is PS stands for static power, and that PWS, PSW and PSC, that is switching power and short circuit power. So basically the power dissipated by the output capacitance is also known as switching power dissipation. So basically this dynamic power dissipation can be formed by the switching power and short circuit power that combinedly will contribute to a dynamic power dissipation. So total power dissipation is static power dissipation plus dynamic power dissipation. That means, and again, dynamic power dissipation can be a switching power and short circuit power, right? Now, what is this? First, we will talk about the static power. So, what is the majority contributor for this static power dissipation? It's a reverse bias leakage, right? So basically this static dissipation is major contribution. And what are its major contribution? First is a reverse bias leakage current between the diffusion region and the substrate. This is the first thing. And second is a sub threshold conduction, right? So the leakage currents are the major contribution or major contributor for the static power dissipation. Now who generates or where this leakage currents comes from? So basically it comes from the reverse bias leakage between the diffusion region and the substrate, and second one is the sub threshold conduction, right? These two leakage current can contribute to and CMOS can have the static power dissipation. Now, what about dynamic power dissipation? So basically this dynamic power dissipation can be mainly because of the two things, switching power and the total capacitances or capacitive load, you can say. So this, what is switching power? So basically this switching power is caused by the charging and discharging the output capacitive load, right? So it is basically because of the charging and discharging of the output capacitive load. And consider, if you consider an inverter, right, that is operated in a switching frequency of f, then how the total dynamic power, that is PD, it has been calculated. So PD is equal to CPD plus CL multiplied by VCC square multiplied by switching frequency. So what is PD? It's a dynamic power consumption. VCC is your supply voltage. It could be a plus 5 volt. Mostly it is a plus 5 volt. VCC is nothing but your VDD actually. F is the transition frequency, or you can say switching frequency. Then CPD, it's a power dissipation capacitance, and mostly this CPD is specified by the manufacturer of that device, and its value lies between the 20 to 24 picofarad, and CL is the load capacitance. So If you know all this and put into this formula CPD plus CL into VCC square into F, you will get the dynamic power dissipation, right? Now, second major contributor of this dynamic power is a short circuit power dissipation. Now, where this short circuit current comes from? So, if you study for a particular interval or at a particular point of in the VTC curve, voltage transfer characteristics of the CMOS, the point or the actually exact the situation will come where the both NMOS as well as PMOS transistor are into a conduction mode or are on, right? So so this input changes very slowly. The point will come where this NMOS and PMOS transistor are on. That means into a conduction. And at that point, the excess power is dissipated due to the short circuit current. Because see, both that means that pull up network as well as pull down network, both are closed switch. That means short circuited. That means the maximum current can flow from the VDD to ground, and that causes the short circuit power dissipation, right? And how you can normally estimate that short circuit power dissipation is PSC is equal to I mean into VDD, right? PSC is equal to I mean into VDD. That can give you the exact value for short circuit power dissipation. Now, the last point of this unit number first is a impact of technology scaling on CMOS inverter, right? See, now why it is require or why it is essential to go for a technology scaling and what is its impact on the CMOS inverter. So that point we are going to discuss. Now, as you know, over the past many decades, this CMOS technology has been a primary drivers, right, of the electronic industry. So uh, nowadays also if you compare the chip size, right, it is continuously goes on reducing. And what is or what can say what is cause behind this? It's a CMOS technology or the technology scaling in another language you can say, right? In a small area or in a single chip, maximum number of transistors you need to occupy, right? As compared to the previous days where uh, to design a very simple circuit also we are requiring a large what you can say large chips, right, on which the transistors can be occupied and all the circuitry is implement on that. But as the technology improves, right, as there is a research and innovation in the CMOS technology, nanotechnology we are talking about nowadays. So basically what happens is the chip size is keep on reducing, right? Whatever the chip size, whatever the board size, right, that keep on reducing, and that is nothing but the technology scaling. Now what is this impact on this CMOS inverter? So over the past few decades, right, CMOS technology scaling is a primary driver of the electronics industry, or you can say it's a prominent area where the electronics engineers are working nowadays. And it has been provided a path towards both denser and faster generation. Denser, why? Because of see, when you say it's a denser, but the area is not increased, right? Area remains the same, only density it is increased, and that is because of the CMOS technology, right? So this scaling technology scaling, right? What are the outcomes of this? So basically, so the chips are become denser and faster integration. The transistor manufactured today that are 20 times faster and occupy less than 1% of the area of those built 20 years ago. As I told you, if you compare the chip size as on today and uh, before the 20 years, right? So the 20 speed, its speed also increased, right, 20 times faster than that of the uh, 20 years ago. And the area on which the transistors are occupying, right, it is a less than 1%, right? So see, in a 20 span of this 20 years, how technology got shifted towards the CMOS, and everything is now very smaller and faster one. You can imagine this, right? So the advantage of this technology scaling is what? Whatever the transistor manufacturers today are 20 times faster, and that can be occupied less than a 1% area of those built 20 years ago. This is the first and very important point. Then what you can talk about is the number of devices per chip. As I told you, the number of devices per chip also reduced, right? If you compare the TTL technology, right, that is the transistor technology, and CMOS technology. So say, I'm just telling it as for an example. If you say, to design a particular chip, if you require 200 transistors, so the same circuit, if you design with the help of the CMOS, so there is a less than, or the number of transistors are required are very less. It is almost around only 60% of that 200, right, with the help of CMOS technology. So the number of devices per chip and the system performance has been tremendously improved, and it is exponentially improved over the last 2 decades. As the channel length is reduced, the performance is also improved. The power per switching event, it is decreased, and the density, that means the capacity to occupy more number of transistor, it is also improved. Now, these are also some of the advantage of this technology scaling, right? Power consumption is reduced, density improves, right? Area remains the same, but density improves. As you are reducing the channel length, that means you are actually modifying the W by L ratio, right? And this technology scaling is nothing but what? See, you are scaling down something, means what? You are actually dividing something. So you are dividing that W by L, each term by the alpha. That alpha is nothing but your scaling factor, right? So this W by L, right, it is goes on reducing. What it shows, on a same area, you can now mount, or you can now implement more number of devices, right? You can now mount, or you can build, or you can implant more number of devices, and that is one of the biggest advantage of this technology scaling. Now, also, as at the beginning only, we have discussed about the difference between BJT and CMOS, right? So CMOS always have a faster switching characteristics as compared to BJT. So in CMOS, we are using a PMOS and NMOS, right? So MOSFET itself has that inbuilt capacity of exhibiting the faster switching speed, right? So as compared to the BJT, obviously the switching, or the switching speed is also improved in case of CMOS technology. Power per switching event is decreases. The density, that means in the same area, the whatever the number of devices that you are implementing, it is also improved. But the power density, total circuit per chip, and the total chip power consumption has been increased, right? So power density, it is increased, total circuit per chip, it is also increased, and the total chip power consumption has been increasing. See, any technology any technology have always have certain advantages and disadvantages. There is no a single technology that have only advantages and there is no advantages. No, such ideal systems does not exist. You can go for with any technology. There are certain advantages, there are certain disadvantages, right? So if you are going for the technology scaling also, that part also have certain uh, advantages as well as disadvantages. So what are the disadvantages? Power density increased, total chip power consumption, it is increased, total circuit per chip, it is also increased. So these are the disadvantages. And what are the advantages? What are the advantages? As channel length is reduced, more number of devices can be occupied, switching speed is increased, performance increased, right, density increased, total power per switching event, it is increased. More number of transistors can be occupied. It requires a less area. So these are the advantages of this technology scaling, right? And the need for more performance and the integration has accelerated this scaling trend in almost every device parameter, right? So now when you have decided to go for this technology scaling, so you have to concentrate and you have to scale for the every device parameter, such as you have to focus on the lithography, you have to focus on a effective channel length, you have to focus on a gate dielectric thickness, supply voltage, device leakage. See, this supply voltage vdd also plays very important role in a technology scaling. If you reduce the voltage required this vdd, you are actually uh, it is the most what we can say the effective, one of the effective option that actually scale down your technology, and secondly it will reduce the power consumption also if you just simply reduce the supply voltage vdd, right? So as a part of this technology scaling, you have to concentrate or you have to accelerate the scaling trends in almost every device parameter, such as lithography, effective channel length, gate dielectric thickness, supply voltage, device leakage, etc. Again, there are many more parameters, but these are the most prominent parameters that you should consider, and you should some accelerate the trends, right? In these parameters also, while consider lithography is a one, so then effective channel length is a second, gate dielectric thickness is a third one, supply voltage, then device leakage currents. So all that you have to concentrate while you are going for the technology scaling. And the some of these parameters are approaching the fundamental limit, right? Means what? Okay, you are scaling down the technology, but there is certain limit, beyond that you cannot scale down. And these some of these parameters are actually they're approaching their fundamental limits, and alternatives to the existing material and structure may need to be identified in order to continue scaling. And that's why now we are shifting towards the nanotechnology, because with the existing technology, though you are inculcating and implementing the technology scaling, but some of the parameters are approaching their fundamental limits. Beyond that it cannot be scaled down, right? It or it is of no use. Then what is the solution to this? So solution is you have to go for some alternative materials or alternative structure, nanotechnology, or in a simple word you can say now you have to take help of nanotechnology, right, to continue with the scaling. So this is about the impact of technology scaling on a CMOS inverter. And this is your last point of unit number first. Okay, so we have finished with the unit number first. uh, we will stop here. Probably in the next lecture we will start with the next unit.